We're doing question number 5, and the first goal of this question is to find the electric field at point P created by the negative charge here and the positive charge here. The way we're going to find this is we're going to find the components of the electric field of both of these and add them together. We're going to use this equation for electric field, and this is the constant E0 used in our equation. So the best way to start is to draw your expected vectors. So from the positive charge, we know the electric field points away. So it will be, the vector will look something like this. And since 8 nanocoulombs is greater than -6 nanocoulombs, which will pull this way, we know this will be slightly larger magnitude than this will be. So we can just expect to see that, and that's a way we can check our work later to make sure that we've done everything right. So electric field is equal to, using this equation, 1 over 4 pi E0, and Q for the negative charge is -6 times 10 to the -9th coulombs over r squared, which is 0.03 meters, times, and this is where the components come in, times cosine of 60 here, and this is our x component, so we're going to put an I hat. For the y component, for the negative charge, we're going to do 1 over 4 pi E0 -6 times 10 to the -9th coulombs over 0.03 meters squared times sine 60 and j hat to denote our y component.
And then for the other charge, we're going to do the same thing as we did for the first one, so plus 1 over 4 pi epsilon naught, except the charge for the positive source charge is 8 times 10 to the -9th coulombs over 0.03 meters squared cosine of 60 I hat plus 1 over 4 pi epsilon naught 8 times 10 to the -9th coulombs over 0.03 meters squared sine of 60 j hat. When you add up all of the I and j components in order to find the final electric field result vector, keeping in mind that anything to the left would be negative on the I hat and anything downward would be negative on the j hat, we get our resultant electric force vector to be about -69922.3 I hat plus 17301.3 j hat Newton per coulomb. Okay, and so once we have our final electric field vector, we find the magnitude of the electric field by using the formula, or by doing the square root of whatever the x component is plus the y component squared, like that. And so when we do the square root of this number squared plus this number squared, we get 72031 newtons per coulomb. And then when we find the theta, or the direction of the vector, we do like theta is equal to the inverse tangent of the y component over the x component. So in this case, inverse tangent of this number over this number.
Okay, so for the second part of this problem, we're finding the force on point P, given that it is -4 nanocoulomb charge. And so this is the equation we used for force, 1 over 4 pi epsilon naught times Q1, Q2 over r squared. Using the constant, epsilon naught equals 8.85 times 10 to the -12th coulomb per Newton meter squared. So at point P, you know that the force from this is an attractive force towards it, and the force from this is a repulsive force away from it. So the vectors will look roughly like this. So to find the force from the -6 nanocoulomb charge, using this formula, the force at point P from the -6 nanocoulomb charge is 1 over 4 pi epsilon naught times 4 times 10 to the 9th coulombs times 6 times 10 to the 9th coulombs over 0.03 meters squared. And similarly for the 8 nanocoulomb charge, it's 1 over 4 pi epsilon naught times 4 times 10 to the 9th coulombs times 8 times 10 to the negative 9th coulombs over 0.03 meters squared. And so these values will be for the negative 6 nanocoulomb. And so these values for the negative 6 nanocoulomb, the total magnitude will be 2.4 times 10 to the negative 4th newtons. And for 8 nanocoulomb will be 3.2 times 10 to the negative 4th newtons. And again, on this vector, this will be from the negative 6, and this will be from the 8, so it's a little bit longer because it's 3.2 versus 2.4.
Once you have your two total force vectors, you need to find the components for each of them. So you're going to have to multiply by sine of 60 degrees to find j hat, and then you're going to multiply by cosine of 60 degrees to find the I component. And you're going to have to do that for each of them. So you have sine 60 degrees to find the j hat and cosine of 60 to find the I hat. 1.2 times 10 to the negative 4 newtons I hat, and you'll get 2.08 times 10 to the negative 4 j hat. And then for the 8 nanocoulomb charge, you'll get 1.6 times 10 to the negative 4 I hat. And for the j hat, you'll get 2.77 times 10 to the negative 4 j hat newtons. And then once you combine these components like we did for the electric field, you'll get the total I hat being 2.8 times 10 to the negative 4th newtons I hat. 6.9 times 10 to the negative 5 j hat. And then to find the magnitude of these, you would just do the square root of each of these squared and add it together, and you'll get that the total force magnitude is equal to 2.88 times 10 to the negative 4th newtons. Once we find the magnitude, we have to find the direction. So in order to find our theta, we're going to do tangent inverse of this component over this component. So the y over the x. So the x-axis.